Welcome back, and welcome to our video on optimization. If you watched the last video, we discussed optimization being in the same group as related rates with just a few minor differences. In this video, we'll be going over my general guideline, which works for all optimization problems, as well as an example problem to show you how my guideline always works. In short, an optimization problem tests your ability to represent a given situation as a function and then find the optimal value of either the function itself or its variable. By optimal, I mean it as a general way to say maximum or minimum value, so don't let that scare you. So let's go ahead and review this general guideline, that way you can go and tackle any optimization problem after this. And afterwards, we'll be going over an example. The main idea behind optimization are these three things. We want to analyze, formulate, and optimize. This is very similar to related rates, just like we discussed in previous videos. But there's going to be a little tweak, some minor differences. So let's go ahead and get to it. When we analyze, we want to make sure that we identify all given quantities and those that we'll solve for. And we always want to include units as well. Additionally, we want to take a second to visualize the situation and draw it if needed, because most times we're dealing with some sort of shape or some sort of diagram that we can represent and label it with our variables. Up next, we want to formulate what it is we're representing. So, we're going to be formulating and writing an equation to represent what is to be optimized. In this function that you create, we need just one independent variable. If you have two, you'll need to write an equation to represent one of them in terms of the other, and it's usually possible. And lastly, which is one of the most important things we do, is we want to go ahead and define an appropriate domain for the variable regarding the situation. And each situation is different, and I'll be going over each and every situation as they come along. Lastly, we want to optimize. So we want to first ask ourselves, are we computing a maximum or minimum? This is very important because we're going to be taking the derivative with respect to the independent variable of that function that we create. And then we'll set that derivative equal to 0. After we do that, we'll just be solving for the independent variable. And that will give us that maximum or minimum value on that original function. But before we say that we're all done, make sure that you always justify that value. Justify it as a maximum or minimum with a sign test on the first derivative or testing the concavity with the second derivative. This way, you can essentially prove that it's a maximum or minimum on that function that you created. And then before you pack up and call it a day, just make sure that you give a conclusive statement with units. And there it is. That's my general guideline on optimization. The more we practice, the more it'll become part of us and second nature. That way we won't need to keep referring back to this little quick guide. Eventually, you'll be able to do problems knowing the process off the top of your head. So as promised, let's go ahead and go over an example problem so I can show you how my guideline always works and helps us get the correct answer each and every time. Suppose a box with an open top is to be constructed from a sheet of cardboard that is 20 by 40 inches, and we're doing so by cutting out squares from each corner and bending up the sides. The question is, what is the maximum volume that this box could have? And like I said, we can go ahead and use this guideline step by step. So let's go ahead and start by analyzing. Let's go ahead and identify all of our given quantities. And let's identify what we'll be solving for. In the problem, I noticed that we are dealing with a cardboard sheet that is 20 by 40 inches. So this is a rectangular cardboard sheet that's 20 by 40 inches. What makes this problem unique is that we're cutting out squares from each corner. So that's pretty unique. And I don't think that we've seen problems quite like this that often up to this point. So I want to go ahead and visualize this situation by drawing it out. And here it is. So I represented some cardboard box, and it is 20 by 40 inches. The corners have squares cut out of them. As a reminder, and this is going to be very useful later, remember, squares have the same length and width. So just keep that in mind. Now we can go ahead and move on to the formulate stage. So, how can we write an equation representing what is to be optimized? Remember, we want to find the maximum volume. This problem states that we want to find the maximum volume. And so, let's go ahead and represent that with an equation. If we're dealing with a rectangular box and its volume, Well, the volume of a rectangular box is equal to the length times the width times the height. The length times the width times the height. So all we got to do is just, well, plug in length, width, and height, and then we'll have the volume. And we'll have our formula for volume. But remember, we're trying to maximize this. So by taking a look at my cardboard box, after we remove those cuts, it's pretty clear that, okay, each dimension or each side had something cut out of it. And it looks like, let's say, let's just go ahead and call those cuts, the length of the cuts, X. So each side of each square is X. We can just call it X. We could use C, we could use S, we could use X, Y, Q, doesn't matter. I'm just gonna go ahead and use X just because it's convenient. So looking at our base, looking at that base, it's 40 inches long, but then we cut out X on one side and X on the other, and this happens at the top and the bottom. So our length isn't 40 anymore. It looks like we have 40, and then we're going to take away a cut from the left and a cut from the right. So our length, we can represent that with 40 minus 2x's, or 40 minus 2x. And this will be in inches, as a reminder. Next, we have our width. Just like our length, we have 2x's being cut out from the width. And our width is 20 inches, and we're taking away 2x's. So we can represent our width with W equals 20 minus 2x. All right, so all that's left is the height. Let's go ahead and check out that height. So height equals, well, what would the height equal? That's a good question to ask. And sometimes it may not be so easy to visualize. But don't worry, I gotcha. Because after we take away those square cuts from each corner, we're told that we're going to be bending up the sides to create that open box. Look at that. After we take away those cuts and bend up the sides, it looks like that square cut, that X, that's our height. And it is. That X is the height because we cut out those those corners that were squares. And so if we were to bend up that side, well, that bend was X inches long. And so it looks like we're in a pretty good spot now because we can completely define this volume function with just one variable now. We've done a really good job of that. So we could represent this function, or this volume function, as a volume as a function of X, because we're using X as our independent variable, is equal to, well, length times width times height. We have defined all three. So this is great. All we got to do is just plug and chug. So we have 40 minus 2x multiplied by 20 minus 2x multiplied by x. This is good. This is good. We have our function. It's represented fully. And we have one independent variable. Now, before we continue to optimizing, we want to make sure that we identify an appropriate domain. Here's what I mean. If we're taking a look at each of our dimensions, our length, width, and height, well, it looks like our height isn't really restricted, but our length and width are. Take a look at that 20 minus 2x, or take a look at our width. If we were to make a cut of, let's say, 10 inches, so each side was 10 inches, this means that our width would be 20 minus, well, 2 times 10, so that's going to be 20 minus 20. This means that our width would be 0 inches, which means that if the width is 0, then the entire volume is 0. And that is not good. Likewise, we can't have a negative cut. So this means that we can't have a negative x. So our x, our domain, let's go ahead and write that out right here. Our domain is restricted. We can't go less than x, so we can include 0 because we can have a volume of 0, but we can't be negative. Likewise, if we were to make a cut of 10, this means our width would be 20, or 20 minus 20, which would be 0. If we go anything beyond 10 inches, we would have, let's say, 11 inches. If we made a cut of 11 inches, we have 20 minus 22. That'll be negative 2 inches as a width. Again, we cannot have a negative distance here. So our domain for x is limited to values ranging from 0 to 10, and these values are inclusive. So now that we've done this, we're ready to optimize. We're all set. We are all set. Let's just go ahead and expand this volume function. That way, when we take the derivative to find the maximum, it'll be nice and easy. So rewriting, our volume function will be v of x equals, and let's go ahead and distribute. So we're going to have 40. So foiling out, I'm going to have 40 times 20. So that's going to be 800. 800 times that x, that's going to be 800x. Then we're going to have our last terms. We can have the negative 2x times the negative 2x. So that'll be positive 4x squared. But that'll be another x, so that'll be positive 4x cubed. And then we want to take care of our outside and inside terms. These are the terms that usually get added together. And so I'll do that at the same time. We're going to have 40 times negative 2x, which will be negative 80x squared because of this extra x over here. So negative 80x squared. And then we'll have negative 2x times 20, which will be negative 40x times an x, which will be minus 40x squared. And so in simplifying, we'll have our volume function as, I'm going to move everything around that way it's in descending order or in standard form. So 4x cubed minus 120x squared plus 800x. And all I've done was just FOIL. I did it in my own unique way. I'm sure you can work this out yourself and get the right volume function as well. And now that we've got this set up, let's just go ahead and optimize. So first, are we computing a maximum or minimum? We have identified in this problem, it is a maximum. So we're good. Next, let's go ahead and take the derivative of this function with respect to our independent variable, which is with respect to x. And so we can go ahead and use prime notation for this because we only have one independent variable. So if we take the derivative of both sides, we'll have v prime of x equals, this will turn into 12x squared, power rule, minus 240x plus 800. There we go. Now that we've taken the derivative, let's go ahead and set it equal to 0 and find that optimal x value, or find that optimal cut in our cardboard box. So in setting this equal to 0, we have 0 equals 12x squared minus 240x plus 800. I'm going to try and make my life easy here by seeing if I can factor. I see that all of these terms are divisible by 4. So let's go ahead and pull out a 4. So we have 0 equals 4 times, that'll be 3x squared minus 60x plus 200. And I believe I did this all correctly. I think I'm good. Yep, I'm good. All right. So up next, here's what we want to do. I mean, this doesn't look like it's easily factorable. So what I'm going to do is, hey, nothing else works. This is quadratic. You can use the quadratic formula. And that's exactly what we should do in this situation. So before we use that quadratic formula, we can just go ahead and divide both sides by 4, which will make our lives a little easier because we won't have to deal with a pesky constant. And so the 4's will eliminate from the right side. 0 divided by 4, well, that's still 0. That is still 0. And so we'll be using the quadratic formula on 3x squared minus 60x plus 200. To save some time, I've already done the quadratic formula for us, and the answer that I received was x equals 10 over 3 multiplied by 3 minus the square root of 3, and I received x equals 10 over 3 times 3 plus the square root of 3. And I'm going to give approximations for these. This first one, this is approximately 4.226497. This other one is approximately 15.773503. I'm using 6 decimal places because I usually don't round. I usually like leaving everything in exact form until the very, very end, because if you are taking AP Calculus, you're going to want to go ahead and round to 3 decimal places at the very, very end. To ensure that you have an accurate answer, just make sure you use exact terms until you're ready to estimate. So getting back to it, checking these numbers out, remember, our domain is from 0 to 10. From 0 to 10, inclusive. this x value, 15.77, would not make sense. That would not make sense because it lies outside the domain. It wouldn't make sense for us to have a negative length for the width here. These two will be positive, but the width will be negative, leaving us with a negative volume. And that is not possible with regard to this situation. So what I'm going to do is this one's gone. Taking this, and it is gone. Or I can just go ahead and erase it and not be lazy. So there we go. That one's gone. This is the critical point that we're looking at. Notice I didn't say that this gives us the maximum cut or the maximum volume. I didn't say that at all. I know that this is one of our critical points, and I'm going to prove that it's a maximum. Like I said, we can do this in one of two ways. We can use a line test on that derivative, on the first derivative, or we can test the sign on the second derivative. To make my life easy, I like using the second derivative just because I don't like drawing if I need to save time. So let's go ahead and calculate the second derivative of v. So in doing so, we can do this nice and fairly easily. We can take the second derivative is equal to, so the second derivative of the volume, that'll just be 24x minus 240 plus 800, that's going to be 0. So we're left with 24x minus 200. Now let's go ahead and input that value. So v double prime evaluated at 10 over 3 times 3 minus the square root of 3. Or we can just input 4.226497. Either way, before we see our answer, note that if we receive a positive answer, this means that the function v, volume, will be concave up. Will be concave up at this point, meaning that that will have to be a minimum. If I receive a negative answer, this means that the graph or the function of v is concave down at this point, which means that 4.226497 will be a maximum of the function. So if we have not mastered that yet, please go right back into curve analysis. We have shown this earlier, so this will work. And so upon computing the second derivative evaluated at that critical point, I received negative 138.56 as the approximation. So it's approximately equal to this. And so because the second derivative is negative at this critical point, and we have established that this is a critical point, it's either a maximum or minimum. This means that this value, x equals 4.226497, or a cut of 4.226497 inches, will give us the maximum volume. So we're not done yet. We're going to have to go ahead and input this value then back into our volume equation to receive that maximum volume. And so upon evaluating this function, our volume function, at 10 over 3 multiplied by the difference between 3 and the square root of 3. So once we input that value, what I received was 1,539.60071. And so we're not done. We need to make sure we give proper units and we make sure that we round. If you're in AP Calculus, make sure you round to 3 units. Everybody else, make sure you listen to your instructor. If they say 2, go 2. If 3, go 3. It's fine. And so then our volume then, or our V max, is approximately 1,539.601 cubic inches. Cubic inches, or inches cubed. We need to make sure we note those units. Earlier we stated we were working in inches, and so our volume, our maximum volume, needs to be in cubic inches. And the reason that this works is because, remember, we're dealing with an x here, or this whole thing is in inches, this is in inches, and this is in inches. So we have 3 terms that are in inches. So inches times inches times inches gives us cubic inches. And so there we go. We're all done. I properly went through my own guideline and showed you that it works for this specific problem. And it does work for all other problems, and there will be other videos with other examples. But what we need to do is start learning how to trust this process, because now that we understand that it works, we need to go ahead and start implementing it in every optimization problem that we complete. That way, we're going to ensure that we are flawlessly completing these problems. So keep watching more videos, keep practicing, and I'll see you in the next one where I'll go over more examples. Have fun.